it's time for our next speaker. So it's my pleasure to introduce Losevich from Rochester, who's going to tell us about a few simple perspectives on Fourier uncertainty. So take it away.
Okay, thank you very much. First of all, I'd like to thank the organizers. It's a tremendous honor to be here. And it's great to see so many old friends. And so yes, I would like to make a few very simple remarks about Fourier uncertainty. And let me begin by motivating this for sort of classical harmonic analysis. So the restriction conjecture says that if you take the operator, which computes the Fourier transform of the function and restricts it to a sphere, that this satisfies certain LP-LR bounds. This is an incredibly far-reaching problem with implications in partial differential equations, geometric measure theory, etc., etc. It's one of the central problems in harmonic analysis. And the two-dimensional case was solved by Zygmunt and Pfefferman in various contexts in the 70s. The general case, in spite of work by many wonderful mathematicians, is still quite open in higher dimensions. So let me begin by motivating the material in this talk by illustrating how the restriction conjecture, restriction conjecture has to say about signal recovery. The signal recovery in this sense should not be interpreted in any practical sense. So let's consider a compact set of, say, positive Lebesgue measure, and the Fourier transform is known except for the delta neighborhood of the sphere. And the question that I would like to ask is, to what extent can we recover the indicator function? Okay. So we write the indicator function as the inverse Fourier transform of its Fourier transform. We split the integral into the known frequencies and the unknown frequencies. The unknown frequencies are in the delta neighborhood of the sphere. Okay? And since we don't know anything about the second term, we estimate it and hope for the best. Okay? So what do? We apply Holder's inequality, and we bound the second term by a constant times the delta neighborhood of the sphere times the measure of the set raised to the power of 1 over p, where what is p? P is the largest exponent that the restriction conjecture affords you. Okay? And if the right-hand side is less than a half, then we can simply go back, take the first term, compute its modulus, and round it up to 1 or down to 0, and recover the indicator function exactly. And the point is that the classical uncertainty considerations give you this with p equals 1. In other words, if the measure of A is bounded up to a constant by delta to the minus 1. Here we can go up to delta to the minus p, where p is the largest exponent afforded by the restriction conjecture. And the point here, and this is largely the theme of the whole talk, is that the uncertainty principle is always stronger in the presence of a non-trivial restriction bound. Okay? So conjecturally, the restriction conjecture goes up to, sorry, I pressed the wrong button. Is the tech, sorry. I should not have pressed buttons I don't know, but that was a laser pointer.
Maybe, yeah, if you just click on the screen.
Click on the screen. Okay, sorry, my apologies. All right. Technology is hard. Okay, so conjecturally, P goes up to 2D over D minus 1, which asymptotically gets closer and closer to 2 as D gets larger and larger. And this gap shows the power of the restriction conjecture over classical uncertainty considerations. Okay, so now let's go to the setting of the finite signals. And let's go over something that I suspect everybody in the room knows very well. And this is the Donahoe and Stark approach to signal recovery. So we have a signal, so let's say it's a function from Z and D to complex numbers. It's transmitted via its discrete Fourier transform. Okay? And the idea is if the whole Fourier transform gets through, then of course we can get the function back by applying Fourier inversion. The question is, what happens if some of the Fourier transform is lost? Okay, so for example, suppose that the frequencies in the set S are missing, unobserved, missing due to noise or whatever, for some subset of Z and D. And the question is, can we recover the signal? And Donahoe and Stark showed that the answer is yes, provided that f is supported in the set E, so that the size of E times the size of the missing frequencies is less than n to the d over 2. And the main tool is the Fourier uncertainty principle. Okay? So here, so these are just the formulas for the discrete Fourier transform that will be used repeatedly in the talk. Okay, so what is the Donahoe and Stark point of view? Okay, so if you have a signal with nt non-zero values, and the Fourier transform has nw non-zero entries, then the support of h times the support of h hat is bounded from below by capital N. This is classical uncertainty principle. So suppose you have a signal supported in E and Zn. I'm just describing it in one variable, though it works equally well in higher dimensions. And suppose the frequencies in S are unobserved. Then what do? If f cannot be recovered uniquely, then there is another signal with the same number of non-zero entries, so that the Fourier transforms agree away from the set of missing frequencies. Okay? So we subtract g from f, then the Fourier transform again has at most nw non-zero entries, and it has at most twice nt non-zero entries on the space side. So by the uncertainty principle, nt times nw is bigger than or equal to n over 2. So if we assume the opposite condition, h must be 0, and that means that we have unique recovery of the original signal. Now, the algorithms for actually recovering the function is a different and very interesting story that I'm not going to discuss here. But for example, by the method of least squares, you can very inefficiently, but obviously recover the function. Okay? And so the Fourier uncertainty principle is, in general, sharp. So there are many ways to see this, but even if n is prime, you can take a subspace. Its Fourier transform is up to a perpendicular subspace. And this shows that the Fourier uncertainty principle in its classical form is, in general, sharp. However, this is what is called a man bites dog situation, right? This happens very, very seldom. It is quite well known that what the critical examples are. They're all subgroups. What is much harder is what are the near extremizers. And the point of this talk is that if in the presence of any restriction estimate, we are very, very far from this scenario. Okay, so this is the theme. All right, so restriction theory enters the picture. So what is the restriction theory in the discrete context? You have a subset of Z and D, and it satisfies the PQ restriction estimate if, again, you have a suitably normalized LQ norm of the Fourier transform over the set S is bounded by constant n to the minus d times the pure LP norm of the function f. If you're not used to this, why is this a correct normalization? Because you can easily check that if p equals 1, this inequality holds by triangle inequality. So this is probably the right normalization. Okay? And here's a first result. So everything in this talk is joint work with Azita Mayeli, who's in the audience. And our first result is the following. So suppose that f and f hat are signals where f is supported in E and the Fourier transform is supported in S. One can weaken these hypotheses in terms of near support, but let's keep things simple. And suppose that S satisfies the PQ restriction estimate with norm CPQ. We're in a finite context, so you should think of all the constants as being concrete numbers, like 5 or 10, and you should think of n as being at least the size of the US national debt. Okay? And so then the conclusion is that the size of E to the 1 over P times the size of S is bigger than or equal to n to the d over CPQ. So if P is bigger than 1, and the constant is a manageable constant, this is a stronger uncertainty principle, which leads to a better recovery condition. Okay. So here is a strengthening of the previous result, strengthening under most circumstances, since there are constants involved. This is not in all regimes stronger than the previous theorem, but here's what it is. Again, f is supported in E, and the Fourier transform is supported in S, and you have a PQ restriction estimate. Then if Q is bigger than or equal to 2, now you have the size of E to the power of 2 minus P over P instead of 1 over P times the size of S is bigger than or equal to N to the D over the constant, and you have a corresponding estimate when Q is between 1 and 2. The exponents are more complicated, but the point is the exponents are still better than the 1 over P exponent you saw in the previous theorem. So the reason this result is not strictly better than the other one is because the constants in the denominator are raised to larger powers. So there are regimes of exponents where the previous result is better. Okay, but again, the theme here is that you get much better uncertainty principle in the presence of the restriction estimate. Now, of course, this begs a question. When does a restriction estimate hold? If the restriction estimate only held in special circumstances, this would not be very interesting. However, this is not the case. So let me first just point out that by applying the Donahoe and Stark method directly, we can recycle all the uncertainty principles that you just saw into exact recovery conditions with suitable constants. Roughly speaking, by reversing the estimates, and the constant of 2 has to do with the fact that we have to compare the signal F with the signal G that we need to rule out. Okay? And I have until 3:05, correct?
Yeah.
All right. So again, the question is, when does the restriction estimate hold? Okay? So there's an absolutely beautiful result due to Jean Bourgain from 1989. He proved that if G is a locally compact abelian group, and you take any n orthogonal functions with L infinity norm bounded by 1, then for a generic subset of 1 through n of size approximately n to the 2 over q, you have an L2 LQ bound. Okay? And with the
it would be abelian group arbitrary orthonormal system.
Sure. Yeah, absolutely. And so the point that I'm about to make is that this result has a built-in uncertainty principle. It comes with an uncertainty principle. And so a consequence of Bourgain's result in the setting of Z and D is that if the Fourier transform of F is supported in S, then for a generic set of size capital N to the 2D over Q, you have this bound, so the L2 to LQ bound, which is just the dual of the restriction bound that you saw a moment ago. Okay? But I promised you a built-in, so this is simply follows from this biduality. So the restriction estimates you saw a moment ago are simply dual to these estimates. It follows by duality, but since you're in the discrete context, it follows by hand in 2 lines. Okay?
Is there a hat on the previous estimate?
No, there's no hat. Oh, wait, I'm afraid to press buttons, but there's no hat. It's the Fourier transform that's supported in S. So there's no hat on either side. So the Fourier transform is supported in the set S, then the LQ norm is bounded by the L2 norm. In the other direction, it's always Holder's inequality. But in this direction, so it's an extension estimate. You can think of F hat as living in the set S, then you extend it to the whole space. So the Fourier transform is hidden.
Thank you.
No worries. No worries. Yeah. Okay. So suppose that S is generic, as in Bourgain's theorem. And suppose that F is supported in E and F hat is supported in S. So Bourgain's theorem implies the following. So we took n to the minus d over q out. We divided by the size of E. And we took out e to the power of 1 over q. So we simply recycled this estimate using the assumption that x is supported in E. But now you just do the arithmetic. And it follows that the size of E is bigger than or equal to n to the d divided by Bourgain's constant raised to the power of 1 minus 1/2 minus 1 over q. So as long as q is bigger than 2, in other words, any non-trivial restriction estimate, or an extension estimate in this case, if you will. And the support of the function is a positive proportion of the whole space. So Bourgain's LQ theorem implies directly that if the Fourier transform is supported in a generic set of size n to the d minus epsilon for some epsilon bigger than 0, then f is supported on a positive proportion of z and d. One can, of course, ask for endpoint phenomena involving logarithmic spaces, etc. All of that is quite interesting in its work in progress. But this shows that the moment you move off of L2, you have this result. And as a simple consequence, if you send a signal f supported in a set of size little o of n to the d via its Fourier transform, and the frequencies in a generic set S are missing, we can recover f exactly with very high probability. Now, if the set S is random, this result follows from Candace-Romberg's and Tao result from a while back. But the point is that it's enough to assume that S satisfies a restriction estimate. So this contains in it both deterministic examples and random examples. The point here, the general philosophy is that if a set is random, then a restriction estimate, a nice restriction estimate is going to hold. But also there are many deterministic sets, spheres, paraboloids, etc., where you also have these nice estimates. And this is why we wanted to come up with a mechanism which allow us to treat both random and deterministic objects within the same formalism. Okay? So I have, in the 2 minutes remaining, let me show you one proof. Let me show you one very simple proof. And this is the proof of the uncertainty principle via restriction. This one is particularly simple and straightforward. So you take a function, write it as an inverse Fourier transform of its Fourier transform. Apply Holder's inequality, just as I advertised in the beginning of the talk in the continuous setting, and bounded by the LQ norm of the restriction operator. Now, by the restriction bound assumption, this is bounded by the LP norm of the function, and the size of S is carried along. Okay? So now we have this situation where the left-hand side depends on X, but the right-hand side doesn't depend on X. Okay? So by the support assumption, this quantity is in fact the LP norm over E times the size of S n to the minus d. And if we put everything together, we again bound the function by the size of S and a suitably normalized LP norm over the set E. So if we raise both sides to the power of P, sum over E, and divide both sides of the resulting inequality by the LP norm, we obtain exactly the advertised estimate, the size of E to the 1 over P times the size of S bigger than or equal to n to the d over CPQ. So more sophisticated analytic methods can be applied to improve the exponents. But the theme, once again, is that in the presence of non-trivial restriction estimates, which is generically true, one obtains stronger uncertainty principles from which one can deduce better recovery conditions. And I'll stop there.
Questions?
Sorry. So this last uncertainty principle, you are showing this f is finite dimensional, or so f belongs to
F maps Z and D, so this is a d-dimensional module over integer modulo n, where n is arbitrary, not necessarily prime. Arithmetic is not being used here, though it can be.
And do you also know something when you can represent this f in terms of like some structured system, wavelet system or something, and then what kind of results you expect?
So we have not worked in detail in the context of wavelets. So in principle, the ideas here can be extended to many orthogonal systems. And this is something that should definitely be investigated. But we have not done that. We wanted to illustrate this in the case of a Fourier basis, because the classical restriction theory comes into bear very, very, very quickly.
But there is one restriction when you use Fourier basis,
Mm-hmm.
because signal analysis, sometimes people look for time frequency localized basis, and the Fourier basis is not a good fit sometimes. That's why you want to impose extra structure.
Sure, though I don't disagree. It's just that it's worth pointing out that since we're not in Euclidean space, complex analysis doesn't get in the way quite as much. You have plenty of functions that are localized both in frequency and in space. So that a priori restriction that exists in Euclidean space is not quite as pronounced here. But I hear you. Yeah.
Yes?
When there are prime numbers involved, sometimes you can put a plus, right, instead of a product.
Yes. Absolutely. So if there is, if prime numbers are involved, then in a one variable case, one can use Tau's uncertainty principle. In higher dimensions, one can use results by Roy-Mishulam, and also there are results that Azita, Jonathan Pakyanathan, and I previously obtained in the context of studying the Pugliese conjecture, which is also applicable here. So when arithmetic structure is present, then one can strengthen many of these results, both probabilistic and deterministic. And I would be happy to describe this if you're interested.
Maybe I can ask a question. Maybe it's a very naive question, but so the Donohoe and Stark result, you can prove a result for when you have any unitary transform, and then you get this coherence parameter, right? So for the Fourier transform, it's 1, right? It's optimally. Right. And would the same thing go through here?
So this is one of several things that we're doing is thinking about this in different contexts, Euclidean space, discrete contexts, different orthogonal systems. It's fairly clear that the general concept is universal, but exactly how to execute it, this is something that we will see in the coming months.
And I'm going to ask one other short question. So you said that the condition for a set to be a restriction set was that for all functions you had the condition you stated, but in your proof it looks like you only need it to hold for one set, right? So
that's true, but this is an extremely, as I'm sure you know, this is an extremely common problem. For example, another problem that I work on a lot is the Falconer conjecture, where you apply analytic inequalities to the study of structures of geometric sets. And one of the problems is that you prove a general inequality, and then you specialize to a particular class of functions. Yes, this is in principle inefficient, but in general, it's very difficult to get around this issue, right? Because one has to, right? Because it's not always easy to improve an inequality for a particular class of functions. For example, you have to identify which class you're working with.
Okay. I think we should thank our speaker again.